Working with data. Every machine learning model you have ever heard about, the recommendation engine, the price predictor, the image classifier, all of them start in exactly the same humble place. They start with a table of numbers. Before a model can learn anything, somebody has to load that table, look at it, clean it up, and shape it into a form the algorithm can actually use. That unglamorous work is what separates a model that quietly fails from a model that quietly works. So in this video, we are going to do the unglamorous work properly. We will load real data sets, split them into the parts a model needs, hunt down missing values and outliers, turn words into numbers, and finally rescale everything so the model treats each feature fairly. By the end, you will understand not just the commands, but the reasoning behind every step. How machine learning sees data. Let's start with how a machine actually sees a dataset, because this mental picture makes everything else click. To a model, a dataset is just a grid, a two-dimensional table with rows and columns. Each row is a single observation. In machine learning, we call that an instance. If you were studying houses, one row would be one house. If you were studying diamonds, one row would be one diamond, and each column is a feature, a single measurable property, like the weight of the diamond or the price of the house. So the whole grid has two jobs. The columns tell you what you are measuring, and the rows tell you how many times you measured it. The number of features is what we call the dimensionality of the data. A table with 9 feature columns is 9-dimensional, even though it prints flat on your screen. That word, dimensionality, sounds intimidating, but it just counts the columns you are learning from. Now, here is the key split that runs through everything in machine learning. Among all those columns, usually one is special, the thing you are trying to predict. We call that the target. All the other columns, the ones the model gets to look at in order to make its prediction, are the features. Keeping these two ideas separate, features versus target, is the foundation of supervised learning, and you will see us physically split them apart in code in just a moment. Loading your first dataset. Time to actually load some data. We will work inside a Jupyter notebook, which is the standard playground for this kind of exploration, and we will lean on a Python library called Seaborn. Seaborn is best known for making charts, but it ships with a handful of clean, built-in practice datasets, and that makes it perfect for learning. The first thing you do is import the library and give it a short nickname, so you don't have to type the full name every time. Then you can ask Seaborn to list every dataset it has tucked away. You get back a tidy list of names, things like tips, penguins, Titanic, iris, and the one we will spend most of our time with today, diamonds. To pull one of these into memory, you load it by name and store it in a variable. A very common convention is to call that variable df, which is just short for data frame, the table object that pandas and Seaborlini use under the hood. Once it's loaded, you almost never want to print the whole thing because some of these tables have tens of thousands of rows. Instead, you peek. There's a command to show the first handful of rows and another to show the last handful. That quick peek tells you the column names, the kinds of values in each column, and whether the data even loaded the way you expected. And the very first habit I want you to build, always check the shape. The shape tells you how many rows and how many columns you have as a simple pair of numbers. The diamonds dataset, for example, comes back as 53,940 rows by 10 columns. Knowing that number up front saves you from 100 confusing bugs later. Splitting into features and target. Now we make that features versus target split real. Remember, we decided the target is the column we want to predict. For the diamonds dataset, the natural target is price. It makes sense to predict the price of a diamond from its physical properties. So price becomes our target, and everything else becomes our features. The clean way to build the feature set is to take the whole table and drop the target column out of it. Whatever is left, carat, cut, color, clarity, depth, and so on, becomes our feature matrix, which we conventionally store in a capital X. Dropping is nice because you don't have to list every feature by hand. You just say, "Give me everything except price." Then we build the target separately. We reach into the table and grab only the price column, and we store that in a capital Y. So now we have two objects. X holds the inputs, Y holds the answer. This is the shape of almost every supervised learning setup you will ever write. Capital X for features, capital Y for the target. And once again, check the shapes. The feature matrix X comes back with the same number of rows as before, but one fewer column because we removed price. The target Y comes back as a single column, just the prices, one per diamond. When those row counts line up, you know every diamond's features are still matched to the correct price, and that alignment is something you never want to break. By the way, there are two common styles to build X. You can drop the target column, or you can explicitly list the feature columns you want to keep. Both get you to the same place. Dropping is faster to type, listing is more explicit about your intent. Use whichever makes your notebook easier to read. Loading your own data from a CSV. The built-in datasets are great for practice, but in the real world, your data usually arrives as a file, most often a CSV, which stands for comma-separated values. For that, we switch to Pandas, the workhorse library for tabular data. You import Pandas, again with a short nickname, and then you read your CSV file by giving it the path to where the file lives on your computer. Once it's read in, you have the exact same kind of table object as before, and all the same habits apply. Peek at the head, peek at the tail, check the shape, but Pandas also gives you a couple of extra inspection tools that are worth knowing. You can ask for the list of column names, which is handy when a file has columns you didn't expect. You can ask for the data types of each column, which tells you which columns Pandas thinks are numbers and which it thinks are text. And there's a single command that summarizes all of that at once: how many non-empty values each column has, and what type it is. That summary is the fastest way to spot a problem column before it bites you. One small but important detail you will notice: a raw CSV sometimes carries an extra index column that got saved along with the data, something like an unnamed counter column. It's harmless, but be aware of it because it changes your column count. Always reconcile the shape you see with the columns you actually meant to load. Why we pre-process missing values. Now we get to the part that genuinely decides whether your model works: pre-processing. Before you train anything, you have to check your data for missing values, for outliers, and for noisy or messy entries, and then deal with them. If you skip this, the model will quietly make unrealistic assumptions, and you'll end up with predictions that look fine but are wrong. Garbage in, garbage out is not a cliché in machine learning. It's the daily reality. Let's start with missing values. A missing value usually shows up as something called NaN, which stands for not a number. It's the placeholder Pandas uses for a blank cell. The first thing you do is count them. There's a command that goes column by column and tallies how many entries are missing in each feature. When you run this on the clean diamonds dataset, every column comes back with 0, which is exactly what you want to see. But real data is rarely that polite. So imagine a messier version of the file where a few cells are genuinely blank. Now you have a decision to make, and the right decision depends on how much is missing. The general convention works like this. If an entire row is essentially empty, if one instance is missing almost all of its values, you usually just delete that whole row, because it carries no real information. But if a single feature is only missing a small fraction of its values, say somewhere in the range of 5 to 10%, you don't throw those rows away. Instead, you fill the gaps. And there are two main ways to fill them. The first way is mean imputation. You calculate the average value of that feature from all the rows that do have a value, and you drop that average into every blank cell. It's simple, fast, and good enough surprisingly often. The second way is regression imputation, which is more sophisticated. Instead of using a single average, you build a small predictive model that estimates the missing value from the other features in that same row. Mean imputation is the quick default. Regression imputation is the more careful option when the feature really matters. Mean imputation, step by step. Let's walk through mean imputation on a real column so it stops being abstract. Take the depth feature in our messy diamonds file. Suppose it has 2 missing values out of nearly 54,000 rows. 2 missing values out of 54,000 is basically nothing, far less than 1%, so deleting those rows would be fine too. But it's the perfect tiny example to learn the technique. First, you isolate the column into its own variable so you can work on it cleanly. Then you compute its mean, the plain average of all the depth values that exist. You'll get a number with a long decimal tail, and it's perfectly normal to round it to 1 decimal place for readability. Then comes the actual fill. There's a single command that finds every blank in the column and replaces it, in place, with that mean value. You peek at the top rows again to confirm the blanks are gone. That's the whole technique. Isolate, average, fill, verify. The thing to internalize here is why the mean is a reasonable filler. By using the average, you're inserting a value that doesn't push the column up or down. It sits right in the middle of what's already there, so it disturbs the overall distribution as little as possible. That's the entire intuition behind mean imputation. Finding outliers with the 3 sigma rule. Now the other kind of messiness, outliers. An outlier is a value that is unusually large or unusually small compared to the rest of the data. Sometimes outliers are real and interesting, but very often they come from data entry errors, and if you leave them in, they can skew your model badly. A single absurd value can drag an average or a slope way off course. So how do you decide, objectively, what counts as unusually large or small? The classic method assumes your feature roughly follows a normal distribution, that familiar bell-shaped curve. If it does, then you can use a beautifully simple rule of thumb. You compute the mean of the feature, and you compute its standard deviation, which is just a measure of how spread out the values are. Then you draw 2 fences. One is 3 standard deviations below the mean, and the other is 3 standard deviations above it. Anything outside those fences is flagged as an outlier. This is the famous 3 sigma rule. Before you trust that this rule even applies, you should look at the data. Plotting a histogram of the feature with matplotlib lets you eyeball whether it really is bell-shaped. If the histogram looks roughly like a normal curve, the 3 sigma fences are meaningful. For our depth feature, the lower fence comes out around 57.5, and the upper fence around 66. Looking at the histogram, nothing falls below the lower fence, so no outliers on the small side, but some values poke out above the upper fence on the large side. You can then count exactly how many rows sit above that upper fence. In this example, it's 366 diamonds. That's well under 1% of the whole dataset, which means it's safe to simply delete them without losing meaningful information. So you redefine the column to keep only the values at or below the upper fence, and the row count drops accordingly. The outliers are gone, and the column is now clean enough to model on. Turning words into numbers. Label encoding. So far, we've been treating everything as numbers, but real datasets are full of words. In the diamonds data, the cut column holds text like ideal, premium, good, very good, and fair. Machine learning models at their core do arithmetic. They can't multiply the word ideal. So we have to convert categories into numbers, and the simplest way to do that is called label encoding. Before we encode, it helps to recognize that categorical data comes in two flavors. The first is nominal, where the categories have no natural order. Think of car color or marital status. Red isn't more than blue, it's just different. The second is ordinal, where there genuinely is an order. Think of letter grades. An A is better than a B, which is better than a C. Knowing which flavor you have matters, because plain label encoding assigns numbers that imply an order, and that's a clean fit for ordinal data, but something to be thoughtful about with nominal data. The mechanic itself is straightforward. You bring in a tool called the label encoder. You point it at the cut column, and it assigns each distinct category its own integer. Ideal might become 2, premium might become 3, and so on. You then store these numbers in a new column alongside the original. A nice sanity check is to count how many rows fall into each category before and after encoding. The counts should match perfectly, which confirms that every ideal became the same number and nothing got scrambled in translation. This whole process of crafting model-friendly columns from raw ones is what people mean when they say feature engineering. Putting features on a level playing field, scaling. We've reached the final pre-processing step, and it's one of the most important, scaling. Here's the problem it solves. Different features live on wildly different ranges. One column might run from 0 to 1, another might run into the thousands. Many models, especially anything that measures distances between points, will let the big range feature completely dominate, simply because its numbers are larger, not because it's more important. Scaling fixes that by putting every feature onto a comparable range. There are two classic techniques, and they're cousins. The first is normalization, also called min-max scaling. It squeezes every value in a feature into the range between 0 and 1. The smallest value in the column becomes 0, the largest becomes 1, and everything else lands proportionally in between. It's intuitive, and it's great when you want hard boundaries on your data. The second is standardization, also called z-score scaling. Instead of forcing the data into a fixed 0 to 1 box, it reshapes the feature so that it has a mean of 0 and a standard deviation of 1. Values above the average come out positive, values below come out negative, and the size of the number tells you how many standard deviations away from average you are. Standardization is the go-to choice when your features are roughly bell-shaped, or when they're measured in totally different units, pounds versus meters versus dollars, because it expresses everything in the same neutral language of how far from typical. Both methods get every feature speaking on the same scale, so the model can weigh them fairly. Summary. Let's tie it all together. We started by learning how a model sees data. as a grid of rows and columns, instances and features. We loaded data both from Seaborn's built-in sets and from our own CSV files, and we built the habit of always peeking at the head and checking the shape. We split that data into a feature matrix, X, and a target, Y, the backbone of supervised learning. Then we cleaned, counting and filling missing values with mean imputation, hunting down outliers with the 3 sigma rule, and turning categorical words into numbers with label encoding. And finally, we scaled everything fairly, using normalization to fit features into a 0 to 1 range, and standardization to center them with a mean of 0 and a spread of 1. None of this is glamorous, but all of it is decisive. The cleaner and better prepared your data, the better every model you build on top of it will be. In the next video, we'll take this clean, model-ready data and finally start training. If this helped the steps click into place, consider subscribing, and I'll see you in the next one.